Hello, everybody. Welcome to the Arithmetic Zone. Unfortunately, Rahsun is out this weekend because he is sick, so I will be filling in for him today with this video on improper integrals. So, one quick thing before we continue is that some portions of this video will be powered by the Desmos graphing calculator. So what are improper integrals? Well, they are a special type of definite integral, but the integrand will be undefined over the interval specified by the limits of integration, which is what makes it improper. So I have this little example here. If we're asked to find the area under the curve of some function f of x over the interval of a to b, I have graphed out here this function, but you can see that there is some sort of vertical asymptote in between a and b. This makes it improper. This is where the function is undefined. So let's look at a more formal example. We're going to determine the value of this following integral from negative infinity to 0 of e to the x dx. So because this limit of integration right here is negative infinity, that is a red flag that this is an improper integral. Anytime you have a limit of integration that is infinite, it is always going to be improper. So let's look at e to the x in the graphing calculator. So we're asked to find the area under this curve from negative infinity, which is all the way back there, to 0. Right there. Excuse that line. So we're finding this area, this infinite stretch of area. This might look like it's touching the x-axis, but it's not. It gets infinitely close, but never actually touches. So how do we address that negative infinity? We can use our knowledge of limits to rewrite the given integral. So we would use a limit statement where t is approaching negative infinity and then swap out that negative infinity for t. And now when solving this right here, we can treat this t as if it were a constant. So because this is a limit, this can yield a real answer or infinity, or it might not exist at all. So if the limit exists and is a real number, the improper integral is said to converge. If the limit is infinite or doesn't exist, the improper integral is said to diverge. So now let's actually solve. So the nice thing about this integral is that the integral of e to the x is just e to the x. So we can rewrite this. We need to carry out this limit statement all the way until we finally sub in. So the limit as t approaches negative infinity of e to the x, evaluated from t to 0. This is going to, if we were to sub in our limits of integration, it would be e to the 0 minus e to the t. And evaluating a little further, e to the 0 is 1, and we're going to keep this e to the t right here unchanged because now we are going to solve this limit. So e to the t, if we were to direct substitute e to the negative infinity, this is really equivalent to 1 over e to the infinite power. And if you have a constant over something that is infinitely large, that goes to 0. So what this is really saying is it's 1 minus 0. So this whole thing is just 1. This integral is set to converge to the finite number of 1, and we can box that out. Now let's look at another example. Let's look at the integral from negative infinity to infinity of x cubed dx. Now this one is different from the last one because both of the limits of integration are infinite, meaning that we are tasked to finding the area under the curve of x cubed over all real numbers. So all of this stretch of negative numbers going on to negative infinity and all of this stretch of positive numbers going all the way to positive infinity. Now that is an arduous task to accomplish. So in order to address this, we need to use our properties of integrals that we have learned in the past. So we can actually split this up into the summation of two different integrals, where one of the limits of integration is a constant. I chose 0 because that tends to be the easier number to work with. So because these two are actually both improper, so we would need to rewrite them using our limit statements. And so we have the limit as t approaches negative infinity from t to 0 of x cubed dx plus the limit as t approaches infinity of the integral of 0 to t x cubed dx. Now keep in mind these t's represent different values. This t is the negative infinity that corresponds to this, and this t is positive infinity and corresponds to this limit statement. Now you could use different variables to differentiate between the negative and the positive infinity if you would like. So now we need to solve these two limit statements independently. And one quick note, if either one of these integrals diverges, meaning that the limit does not exist, then this whole integral is also divergent. So now let's solve. These two integrals have the same integrand, so they will actually have the same antiderivative. It will just be evaluated at different endpoints, this being from t to 0, where t represents negative infinity, and this being from 0 to t, where t is positive infinity. So now, if we were to evaluate, we would get 0 minus t to the fourth over 4, subbing in the 0 and the t to get this, and then plus the limit as t approaches infinity of t to the fourth over 4 minus 0, plugging in those values. So 0 we can ignore these zeros. And so this would be negative infinity. We need to keep this negative out front. So negative 1, let's do negative 1 times to really drive home the point. So negative infinity to the fourth power over 4. This would give us negative infinity, because negative infinity to the fourth power is infinity, divided by 4, that's still infinity, times the negative 1 will give us back this negative infinity. And if we were to direct substitute this infinity in, we would get infinity to the fourth over 4, which is just infinity. So these two limit statements didn't give us like a finite answer. It gave us infinite values. So that means that these two limits do not exist. And because that is the case, the overall limit, our original limit, the integral from negative infinity to infinity of x cubed, is said to be divergent, meaning that there's no way to calculate the area under the curve over those given bounds. So let's go on to our last example. This one is different from our last two because none of our bounds are infinite. So to the unsuspecting eye, this just looks like a normal definite integral. But do not be fooled. We're going to rewrite this as sine of x over cosine of x. And in order for an integral to be improper, it needs to be undefined over the interval. And what's going to make this undefined is if this cosine of x is equal to 0. Now, cosine of 0 is 1, so that doesn't give us any problems. But cosine of pi over 2, if you remember from our trigonometry days, that's actually equal to 0. So at this endpoint right here, the function is undefined, which is a problem. That's what signals to us that this is an improper integral. And we can back this up graphically. You can see, like right here, it's about 1.57 where pi over 2 is. There is some vertical asymptote here. The integrand is undefined at pi over 2, so we need to address this using limits. So now we would write our limit statement, replacing pi over 2 with our variable t, with the limit as t approaches pi over 2, and we're keeping the inside guts the same. And I kept it written as sine of x over cosine of x instead of tangent, because this illustrates that we need to use the u substitution. And so I have our u substitution work right here. I don't feel the need to explain it because Rahsun has a video out already on u sub. So if you're not too sure on what to do, make sure to check that out. And so I rewrote everything in terms of u. So if u equals cosine of x, I'm going to plug in this x value, t, into here, and our 0 into here as well to get cosine of t and cosine of 0, which is 1. And that's why the limits of integration have been changed, and it's 1 over u du. We are completely in the u world. So now we can evaluate this. The integral of 1 over u is ln of u. We have to remember this negative sign here because when we were doing our u sub, we had to pull out a negative from that sine x, and that has to stay consistent. So this negative is going to stay with us until we completely evaluate. So ln of the absolute value of u, and we're going to evaluate that at cosine of t and 1. So now if we were to write it out as our subtraction statement, we would have the limit as t approaches pi over 2 of negative ln of the absolute value of cosine of t minus negative ln of 1. Now the negatives can cancel out, and so we're just left with ln of 1, which is 0. And now we have negative ln of the absolute value of cosine of t. So now we can direct substitute this value in for t. So we have already established that cosine of pi over 2 is equal to 0. Whoops, of pi over 2 is 0. So really what this is saying is we're trying to find negative ln of 0. And if we know our ln graph, I'll draw a quick sketch. It never actually touches 0. It's undefined at 0. There's a vertical asymptote at 0. The ln function is only defined for positive numbers. So this limit does not exist. We can put d any. And because this limit doesn't exist, the overall integral is divergent. And when it is divergent, you need to write out the term divergent. If it is convergent, you don't have to write out that it converges because the fact that it has a finite answer is evidence enough. So that's going to be it for this video. Thank you so much for watching. If we don't have a video next weekend for the holidays, I just want to wish you guys happy holidays. The team at Arithmetic Zone appreciates all of your support. Thank you so much.